The paper of the day is BlinkDB, queries with bounded errors and bounded response times on very large data. BlinkDB is massively parallel database that provides approximate results for queries over large data sets. BlinkDB's distinguishing feature is providing the opportunity for users to trade response time for query latency. Partial results are returned with the annotated error bars, describing their accuracy at the current point in time. Any sample-based query processor needs to decide what types of samples to create. BlinkDB makes the assumption that the frequency of columns used in grouping and the filtering remain static over time, while the exact values being queried on are predictable. In the rest of the paper, the term query column set or QCS describes the set of columns used in grouping or filtering query. For example, if 5% of prior database queries grouped on one column city, then we assume that 5% of future queries will also group on the same column. Given this assumption, BlinkDB is implemented using two main components, an offline sampling module and a runtime sample selection module. Approach. In BlinkDB, uniform samples are generally created in a few hundred seconds. It is because the time taken to create them only depends on the disk memory bandwidth and the degree of parallelism. On the other hand, created stratified samples on a set of columns takes anywhere between 5 to 30 minutes depending on the number of unique values to stratify on, which decides the number of reducers and the amount of data shuffled. BlinkDB is built on top of Hive query engines that supports both Hadoop and MapReduce, and Spark via Shark at the execution layer and uses Hadoop distributed file system at the storage layer. So as you can see from the figure, there is Hadoop distributed file system. On top of it, there is a sample creation and maintenance. And then on top, there are 4 layers: Hadoop MapReduce, BlinkDB Metastore, Spark, Hive on Spark called Shark, then there's uncertainty propagation, sample selection, Hive query engine, and BlinkDB query interface. BlinkDB treats the creation of samples as an optimization problem for each QCS. A key point about the samples is that they are stratified, meaning that rare subgroups of data are sufficiently represented so that queries for rare data still results relevant results. The optimization takes as input the sparsity of the data, characteristics of the workload being run, and the storage cost of the samples taken. The sampling algorithm defines a sparsity function that accounts for the rarity of the items in the data. Workload is defined as the frequency of queries on this data set being run. Storage cost is calculated as the number of rows being stored. Runtime sampling. Given a set of stratified data samples, the BlinkDB query engine is responsible for selecting the samples to run to answer the query. Given a query, the goal is to select one or more samples that meet the time or error constraints the user provides, and then answer the query using these samples. Sample choice primarily depends on the set of columns that are being queried for. BlinkDB uses this information to select samples from the cluster by providing samples that have a high selectivity, defined as the ratio of the number of rows selected from a sample to the number of rows in the entire sample. Once the initial set of samples is decided, the runtime engine selects a sample and picks up a subsample of it that meets the predefined query response time for this request. The subsample chosen also affects the accuracy of the queried results. To determine this accuracy, an error latency profile or ELP is computed based on the selectivity of the query and the response time constraints. Lastly, one of the subsample is chosen. BlinkDB adjusts for any statistical bias attributed to using stratified samples. Performance. TPCH workload. Paper ran a smaller number of experiments using the TPCH workload to demonstrate the generality of their results. With respect to the standard benchmark, all the TPCH experiments ran on the same 100-node clusters, 1 terabyte of data with a scale factor of 1000. Conviva workload. Conviva data represents information about video streams viewed by the internet users. They use query traces from their SQL-based and ad hoc querying system, which is used for problem analysis and data analytics on a log of media accessed by Conviva users. Looking at the contributions, authors use a column set based optimization framework to compute a set of stratified samples. Their optimization takes into account the frequency of the rare subgroups of the data, the column sets in the past queries, and the storage overhead of each sample. Authors create error latency profiles for each query at runtime to estimate its error and response time on each available sample. This heuristic is then used to select the most appropriate sample to meet the query's response time or accuracy requirements. Authors show how to integrate their approach into an existing parallel query processor framework, Hive, with minimal changes. Authors demonstrate that by combining these ideas together, BlinkDB provides bounded error and latency for a wide range of real-world SQL queries, and it is robust to variations in the query workload.